Hello and good evening to everyone. We're just gonna be doing a basic balancing of equation right now. So we're just gonna be deriving an equation based from our question in here. This is our question. It's not directly the same. It's kind of similar to the ones we had in our assignment. So yeah, it's just to have other students that was asking me, oh, who were asking me about this one. Yep. So we have here a given: air is flowing through a nozzle in a rocket. Let's illustrate it. So let's say this is the nozzle. The inlet conditions are 850 kPa. So we have pressure. We're not gonna solve it. 520 Kelvin, so that's the temperature, and we have 30 meters per second, or our let's say velocity. So while the target exit velocity is 400 meters, so we have v2 at atmospheric pressure. So we have p in here. It's looking for the exit temperature, which is our T2. So what we're gonna do is we're just gonna derive the formula. I'm just gonna help you. So it says that assume the nozzle is adiabatic. So let's say that this is a very insulated one, and Q is equal to 0. No heat transfer happening. So let's write our Moeller formula. Um, we use this formula in thermodynamics to compute for an unknown. Mhm. Mm, Bear with me for a while. Bear with me for a while I write this down. Squared over 2. Okay, so this is our mother formula. So heat minus work is equal to summation of m out, mass out, and this is h. So this is our enthalpy plus v squared over 2 plus gravity. Right. So now we're gonna be deriving our formula based on our question. So let's use our marker here. So first we're gonna derive the question. So it is flowing through a nozzle in a rocket. We have an inlet and an outlet. So there is no given specific mass that's coming in or out. So let's assume that the flow flow is continuous. Yeah, it is continuous. It doesn't stop. So m out is equal to m in. So how much we're putting out, that's also how much we're putting in inside this nozzle. So we're gonna cancel it out. Next, there's an indication that there's a work done. Oh, sorry. It's supposed to be for this one. So there is no summation for mass out and mass in. Then um there's no heat exchange going on, since it's clearly mentioned that our nozzle is an adiabatic process or system. So there's no heat coming in or there's no heat going out. So that's also cancelled. Now, what else do we have? We have the work, we have the enthalpy, we have the velocity, and we have the gravity. Now, we also don't have anything mentioned here about any work, any piston, any spring doing the work. So, or a heater, something like that, or something that's pushing or propulsing our air in the nozzle. So we're gonna cross it out. So what do we have here? Oh, so we still have the enthalpy, velocity, and the gravity and height. So it doesn't mention that our system is arranged horizontally, vertically, diagonally, or whatever. That's gonna give us any reason to think that there's a change in potential energy. So we're gonna cancel it out. So now what we have here is um bear with me for a while. H n plus v to n over 2 is equal to h out v to out over 2. Now, are we done? Almost done. Uh, we're almost done. So, since we're dealing with air, we can use the ideal gas law to analyze and solve this equation. Not specifically the ideal gas law, but we're going to consider that this is an ideal gas. So, which what things we can measure in here? So we can measure this V since it was given to us. Now, can we measure enthalpy? Well, maybe in another form we can measure enthalpy. So since enthalpy is a function of temperature, sorry for this one. Yeah, since since this is a function of temperature, we can swap this enthalpy with something a little bit more simpler that was presented to us. So we have here 520 Kelvin. So that's temperature, and based on our previous lessons or previous studies, we can also learn that given temperature and the unknown, which is air, might be air, oxygen, nitrogen, or any um, ideal gas or whatever substance it is, it has its own specific heat capacity, and enthalpy is equal to this too. So we can substitute specific heat and temperature for our enthalpy. So we can rewrite our equation as CP T1 plus V squared over 2 is equal to CP T2 plus V uh, squared over 2. And this is 2. This is 1. There we go. So we're going to erase this one on top so we're not going to be confused. And there we go. This is now our formula, and all you have to do to solve the equation is to just rearrange it. You're looking for the T2, so just bring it out, rearrange it. So yeah, I don't want to give the complete answer. I don't want to, no, I don't want to be asked by our professor. So yeah, that's just one of the simple guides on how you can deal with this problem. So it's not exactly the same. I tweak some of it so you can figure it out your own. What did I change, or what's different? So yep, that's it for now. And again, thank you for listening, and good luck to our upcoming examination. So goodbye.